You guys can see the paper?
Yes.
Okay, great. All right, hi everyone. So today we are going to talk about this paper Dynamo, which is Amazon's highly available key value store. But just before we start with the paper, just a brief introduction to what these sessions are about. So my name is Deepi Agarwal, and this is our second session of the Wednesday series of book club. Um, our regular sessions are on Saturday, where we are going over this book called Designing Data Intensive Applications by Martin Kleppman. And we thought of starting this Wednesday series with the goal of taking some time to, pick up one of the references or articles at the end of the book. And from any of the chapters that we have covered so far in our Saturday's session, and then maybe, share with the group here some of the learnings. So, and one of the key ideas there was whatever content we are reading in the chapter, it's interesting to see how some of those ideas are actually implemented in real world systems. So that was the motivation behind starting with this series. And talking about this paper particularly, so we are right now on chapter 6 in our Saturday's series, which is a chapter on partitioning. And this paper was mentioned as one of the references at the end of chapter 5, which was replication. So the reason, and last week we actually covered a paper on Google Docs, like how they do collaborative editing. And it talked about some of the conflict resolution approaches. So if you are interested in, checking that out, you can check one of our videos. And this paper today is interesting, not just from technical aspect, but also the fact that it actually combines a lot of distributed system techniques, and it gives you a good insight into how those concepts of partitioning and replication are actually used within Amazon. So I thought it's a nice introduction. Now, one disclaimer before I go further is, like I mentioned in my message earlier, that this is a pretty long and dense paper. So if you really want to understand each and everything, I think that might require another session. I won't be able to go over every topic, but yeah, we'll talk about some of them here. All right, so with that being said, let's get started with the paper. So this paper actually, so Dynamo, first of all, has anyone read the paper partly or?
No,
No, not really.
I'm looking for the first time. Yeah.
Yeah, okay. Yeah, so so Dynamo is actually, Dynamo and DynamoDB, I mean, they're two different things.
Okay.
And Dynamo is a distributed storage that is actually used within Amazon internally, and that serves as the foundation of lots of other services within Amazon. So it's kind of a fun fact not to confuse it with the DynamoDB. But what is Dynamo? Like it says, the title, it's actually a key value store, distributed key value store. And it was actually designed with a very specific goal in mind. And that goal was that you want to have your rights, like highly available rights. You want to support that feature. And when I say that you want to go with highly available rights, there are two key terms there, right? When I first is highly available, and the second is you are basically the question is what happened? What are the consequences that you have to, or trade-offs that you may have to make if you go with this feature? And we'll talk about some of that. But in terms of feature, it is basically about building a distributed storage system that supports high availability for writes. And second is there are some SLA requirements, given that it is going to support a lot of Amazon features, including shopping cart and bestsellers list. It also tends to focus on low latency. So That is number two. And the third is uh, it is going with the key value store because a lot of services which actually use the storage system do not require any complex, interrelationships and all of that. As long as you know the key of the item that you're trying to retrieve, you can, retrieve its value or the feature set. So that's where having a basic model as key value store, which can also help you with scalability, was the chosen, was the choice for Dynamo. Feel free to just interrupt me anytime if there's a confusion. So
Yeah,
yeah,
so one question.
yeah.
So when you say it's a key value storage system, so but you are saying this is not a database, right? So
Right.
is
So
it
right.
uh-huh.
Yeah, go ahead.
So is it not a database?
So
That is my question, yeah.
right. So the thing is that's a good point you raised. So the way I look at these two terms, data store versus database, I think database comes with a lot of additional things, right? Like all these, sometimes database people tend to think of, I don't know, like ACID requirements or, concurrency or something. Like I think initially database was fine, but when these simpler data models came in, there was another term, data store. So it is a simpler form of database. I think that's where they call it just a storage model and not particularly a database.
But is this a persistent one?
Yeah, it's a storage model that way.
Okay.
But when you look at, I think DynamoDB is what, I think people refer as database. But I may get back to you with, more precise answer. But my thought process on the top of my head is um, the reason it's not called a database because possibly databases include a lot of other things compared to a simple storage model.
Okay.
Like databases are more than storage.
No problem.
Yeah. So
Hey,
yeah.
hey, sorry guys, this is Flavio. I joined a little bit late. Thanks first for the meeting. I have just one question, actually, this in this initial talk, right? So there is a open source project from Netflix whose name is Dynamite, and the idea is that like Dynamite makes like any database. When I say any, there is like some restrictions, but let's think for example about Redis, right? It makes like any of those database like highly distributed. How it does this? Every request, let's say every write command that you send to the Redis, right? First go on Dynamite, and then Dynamite can sync this write between those different Redis instances. So if one Redis instance, let's say, goes down, you always have a replica of this, key value in another Redis instance, right, which is available. Is there some similarity with Dynamo here? I mean, what is the difference? Do you know about
Yeah,
this?
so I am not familiar with this, the other system you're talking about, but the way you described it, right, that if a write comes in and how it handles like, this, if one of the node is down and how it handles all that. So that is included in this model as well. Like Dynamo also handles, because it's a distributed data store. So
Okay.
when writes come in, if there is a failure, node is down, it does have algorithms to handle that, replication and all of that. But if you're asking specifically what is the difference in algorithms, I'm not familiar with the other system. So
Okay.
yeah.
But I mean, Dynamo is not a layer that you can apply on top of, let's say, other, persistent store. I mean, it's a
No.
persistent store by itself,
Yeah.
right?
Right. Yes.
Okay.
Yeah. Sure.
Okay. Thank you.
So yeah, so we talked about data model, and now let's get into the so first thing I want to touch on is before getting into all this fun stuff about consistency and replication, let there is one thing I want to highlight. So one of their design goals was they are very particular about service level agreements. And the reason I want to bring this up specifically is I think we kind of all of us would know what SLA is, that you want to, respond to a request within a bounded time. And there are, that there is a limit to that. So that's what service level agreements would require. But what I found interesting reading this was, like I said, the theme of our series, Wednesday series, is to club the things that we read in the book and see how they are applied in real systems. And they actually mentioned one of the things that is mentioned in chapter 1 of the book. So this was about that when you are defining SLA, Amazon is not just looking at average or median, but they're actually going with percentiles, right? And they gave a specific example that it's not just about the majority of users who needs to be satisfied, but also if there is a, user with a, for example, they talk about somebody's making a lot of purchases, right? So the personalization, the history of that user would have much more data than someone else who is not, really visiting site or making a lot of purchases. So Amazon will be concerned. So now if they want to run personalization algorithms, right, on their customers, somebody who's making a lot of purchases would have more data to be processed. So they don't want to lose that customer, of course. That's, that's one of the things. And that's what dictates them that they don't want to limit themselves to just average or median, but they also want to go to higher percentiles. So, I mean, this is kind of a very basic thing if you think about it, but I specifically wanted to point it out because of its connection with the things talked about in the book. So with that being said, let's get on to the real fun stuff here about all these algorithms. So the things so Dynamo talks about if it has to be a distributed system and something that has to support scalability, it uses this algorithm called consistent hashing that we'll talk about. And then, of course, given distributed nature, it has to make sure it's fault tolerant. And for that, it works with replication. And they also talk about how they, how they ensure high availability for writes, even when you have a replicated database. And we'll go into details of all of that. There is this discussion about sloppy quorums technique, which again we covered in our book club. So it was nice to see it mentioned here. How many of you are familiar with these terms? Does any of these terms sound familiar, or you have worked on any of them?
Yeah, actually, I've been hearing them in a book club, and I'm trying to read them through this book.
Right.
Yeah. So generally, yeah, I'm aware of most of them, right? Yeah.
Okay.
Yeah, even me, I'm aware of most of the terms here, but this is my first book club meeting.
Oh, okay. Okay, great. Welcome.
Thanks.
So yeah, so let's go over them then. So let's see. So they talk about replication here, but I want to first talk about partitioning. So they talk about their design considerations here, right? What are the features? Like we talked about general, you want to maintain high availability for your writes. And then further they drill down into what specific algorithms they need. So they're talking about replication. They're talking about how will you handle, the latency. For example, if you have a replicated database and you issue a write on one of the nodes, now what are the choices you have? Either if you replicate it to all the nodes which are in your application cluster, and if you do that, there are challenges involved. There is a challenge of latency, right? You have to wait for all replicas to respond. There is a challenge that what if one of the replicas fails, then how long are you going to wait? So there are all these challenges that comes in. So they need to take care of that. And then of course, with replication, there is this concept of conflict resolution comes in. So I'm just throwing these terms right now. We'll be talking about them, but these are the main ideas. Like these are, when you say design considerations, these are the things they have to, these are the challenges, right, that they need to resolve. And then, so this was interesting. Apart from these design considerations, there is also, so we talked about incremental scalability. So you basically want to, do it in a stepwise manner, like you are adding one node or at a time, but you do want to have a scalable system. Symmetry was an interesting point, which says basically that all the nodes have the same set of responsibilities. And what this means to me was that when we were reading the chapter on replication, if you think about replication, there are different architectures for replication. You can have a single leader and multiple followers, or you can have multi-leader replication model, or you can have leaderless. What leaderless, and this symmetry to me sounded to me like leaderless approach, which means that there's no like one or two nodes who are in charge of, accepting rights, but any node you can submit your rights.
Sorry to interrupt. Just a question. But then, if you don't have, let's say, a leader, you need to establish some consensus algorithm here, right?
Right. So they talk about this, gossip protocol and, all these algorithms that they are using, consensus algorithm. I think, I'm not sure if they specifically mentioned Paxos, but I believe that would be the general. But yeah, they use all of those.
Okay.
And then this was another point on heterogeneity, which was interesting. It will come particularly when we talk about consistent hashing. So let's hold on to that for now. So now let's start with, okay, so you have a large amount of data. So of course, one or two nodes will not suffice. So what you do is you have a distributed system, but now you basically partition your data, right, across different nodes. And the standard ways of partitioning are like, let's say if you go with hash-based partitioning, you put your data on different nodes. And when, let's say, a key comes in, you calculate hash and then you write to that node. Or if you have to read that key value, you compute its hash value, and then you refer to that node. So this is like the basic, partitioning or sharding approach. But what they use is this idea of consistent hashing. Does anybody know how this works or wants to?
Yeah, I don't know if you can go over, that would be good.
Okay, sure. So, let's go back to our basic hashing based partitioning, right? We are having, let's say, 7 nodes, right? And we have a set of keys. The way you would kind of organize your hash function is one can be modulo based hash function, right? So when your data comes in, let's say you have a value 14 comes in. So you do the modulo with 7 and you store it in that node. So now the problem with that model is if one of the node goes down, right? Or what happens when you want to add another node? Then your whole modulo based operation means that all the nodes needs to be, the data needs to be moved through your whole, the cluster, the system. Because if you think about your modulo operation, it will just shuffle all the data. If you had 7 nodes first, now if you have 8 nodes, your modulo operation will change everything. So what consistent hashing does is, it's a way to actually achieve incremental scalability. And what I mean by that is, it tries to minimize the amount of data shuffling that needs to happen when a node is added or removed from the cluster. And how that happens is, so basically think of it like this. So usually they try to explain it in the form of by modeling the nodes in the form of a ring. So let's say the way they are showing in this figure here, right? So let's say a key K comes in, right?
Okay.
don't worry about this message here for now, but just to explain the message of consistent hashing, when key k comes in, when it computes its hash, if it falls in this, let's say hash value lands here at a data point, then it will map to the node, which is, let's say, the clockwise fashion next to it. So it goes, right?
Okay.
Yeah. So it goes to node B. And similarly, key comes in, which lands here, it will go to node D. Now, what do I mean by, let's say a node goes down? Let's say a node C goes away, down, right? Now, when that happens, if a key comes here, or let's consider B goes down because key K is labeled. So let's say node B goes down. What will happen to key K? When it comes here, according to this algorithm that I was explaining, that it will just map to the node in the counterclock, in the clockwise direction, right? So if B is down, it will just go to C.
Okay.
Right?
Yep.
So you're basically, your whole cluster is not affected, right? Whereas earlier, when your B goes down, now your number of nodes have gone to 6 and your module has changed everything. Make sense?
Yeah, makes sense.
So that's the idea of consistent hashing, that you want to kind of minimize the impact of addition or removal of a node from the cluster.
I have a question here. So what is this on? I mean, what if all the keys end up in this area between A and B? Like, isn't one node going to be overloaded?
Right. So that's a good question, right? So what the definitely it will happen that if B goes down, the load on C will be higher compared to others, right? Because it is also in the load of B. But going back to your question about what if all your keys land in this, I think that goes back to the point that how you are actually placing your nodes in the first, originally. For example, if you just create all the nodes like, next to each other and here, that won't be a good placement. That is something you have to keep in mind, that, what is how to kind of evenly distribute your nodes in that ring.
Okay, so is it like a range, like from here to here?
Yes,
Okay.
correct. Exactly. So that's, I should have mentioned that. So what you do is you take the range of your hash function and then, so that is what your ring size is.
Got it. Okay.
Evenly distributed.
Makes sense. Thanks.
I have a question. So whatever the range be, the ones between A and B would always fall into C, right?
Yeah, when B is down. Yeah.
Yeah, then it comes back to the same question that Ankita was telling, that C would be overloaded. It doesn't have to be in the same range or the continuous range. It could be small pieces of different ranges that C handles. But even in that case, then C would be overloaded with all the ranges that B used to handle before.
Exactly. So you can't, I mean, and we'll come to that, how to kind of, alleviate that situation. But this is more of, I see this as a trade-off, right? Do you want to disturb your whole cluster versus can you, and you also assume that while C is taking the load, given your service level agreements, B should come back, right? Or you can place another node again.
And when let's say that now B came back, right? Do I distribute the previous, let's say, range that was going to C again to B? Like let's say while B was down, I started, I don't know, 10 keys on C. What happens with those 10 keys on C? Because originally they should belong to B.
Right. So, okay, that's a good question. So the point is, when B was down, things landed in C, and now B is back. So what happens to those things that landed in C, right?
Yes, exactly.
I'm thinking, I have another thought coming to my mind, but I'm not sure if that is how it kind of they are doing it. I mean, in general, I know about this idea about this, sloppy quorum and hinted handoff, where things like this happen, that when a node is down and some other node took the responsibility, and when the original node came back, then it actually gives it back, like,
Yeah. From what I remember, we would get all the ones that it used to have before, but that would happen in the background.
Okay. Okay.
Yeah, because otherwise you can create a situation that your keys now are unbalanced, because C has much more keys than B, because it was handling everything for B while B was down.
Right.
And even then there would be replication, right? Like it's not
Actually,
just handling that. There would be other nodes who have same data as C, and when B comes back, then while C is handling the
asynchronous synchronization. Yeah.
I think I have an idea here, which is derived from distributed hash tables. When a node dies and it comes back, what happens is a new join process starts. So that node is going to hash again to find his position on the ring, and then he starts negotiating and getting his share of the keys for which he is going to be responsible. It's as if it is a new node on the network.
Okay.
So in case B dies, B comes back, talk with C. C says, okay, here is your keys.
Right.
This is the data, and the node, the overlay network.
Coordination involved. Yeah.
Yeah.
So right. What you're saying is a kind of, let's say, B, C, or whatever. They actually don't exist per, let's say, an ID. They are kind of immutable, right? So like whenever the node come back again, it's like adding a new node in the ring. So
yeah. Usually they take the same keys because they hash their IP address or the MAC address of the node. So they always get the same portion of data in the ring, in the same position in the ring.
Okay.
So that's what sometimes is a little bit confusing, because it seems like that a lot of negotiation happening to make that node goes back, but in fact is just joining as a new node.
Okay.
Okay, so the position is very important. So it comes at the same position. Okay.
That's interesting.
Yeah. Thanks for sharing that.
Yeah. Thank you.
But how do we guarantee the position in that case?
I think by the MAC address, that is what you're saying.
Oh, it's like or by the consistent hash
information,
it automatically happens that way. Okay, makes sense.
Or any property that is not, say, dynamic, right? Can be.
Yeah. Interesting. Okay. Yeah. Thanks everyone. Learned new stuff. So so that was this algorithm about. Now, one of the things they also talk about is we also have to keep in mind that what if, nodes are not all of the same capacity, right? There is heterogeneity. That's what I was referring to earlier. So we also have to take into account that the heterogeneity among nodes, right? C may have more processing or storage capacity than B. So it doesn't make sense for them to have the same amount of load, right? And for that, they talk about that they are taking that into account to actually position them accordingly. And they talk about this concept of virtual nodes. So what they say is, let's say if C is a higher capacity one than B, then they try to actually have this concept of virtual nodes. So which essentially is saying like put two markers on the ring and mark them that, C is the owner, right? So C is responsible for picking keys for two sets of keys, basically, compared to B, which may be responsible for only one set of keys, right? So that's the concept they refer to as virtual nodes, and that can take care of the different capacities.
So what you're saying, let's say, for example, let's say B has more capacity than C, right? So what you're saying, if I understood well, is like you put, let's say, this virtual node between B and C, and now whenever you know, some key goes before this virtual node, but after B, it's actually lands on B.
Right, right.
Okay.
Correct. So that way it can take more load.
Okay.
Yeah. So that was about, oh, and the other thing is when we are talking about distributed system, this is like we talked about partitioning, but also we have to, like, usually partitioning and replication go together, given distributed nature of the system. So you would, they have given example that, you know, certain key would be replicated to, you know, would be replicated to multiple nodes in the cluster. And that's where I think even the original question we had about that when B comes back, it kinds of, you know, can also relate to that question that when B comes back, let's say B, C, and D were forming a replica. And if B went down and when it comes back, maybe it has to synchronize with the other copies to get back to its original state. But that's the question, right? If B is treated as a new node, then something to look at, like how we handle the replication module.
And you mentioned about replicas only between B, C, and D. I mean, or are we talking about replica in the, you know, the overall ring?
No, overall, I'm saying B, C, D, and was just an example.
Oh, okay, okay.
Yeah, yeah. But yeah, because we don't want a data set to be only on one node. So, so that was the idea there. The other thing next is, so we talked about partitioning here and virtual nodes, and then they talk about replication, which really opens up a whole different set of interesting points. So when you talk about replication and these different architectures, right, leaderless and all that, let's go back to our fundamental requirement for the system, which is highly available writes, right? So anytime a user wants to write something or update something, they want the system to be highly available, which means that given the basic theorem like gap theorem, if you are having a highly available system and fault tolerant network, you want a fault tolerant system. So you have to compromise on consistency, right? So you may get stale data on and off, but that's a trade-off that the system makes. Now, even talking about writes, when you are, and if you have like multiple replicas, one of the ways to support writes is you submit a write to a node, you don't give confirmation to the client until all the replicas are in sync, which we don't follow here because we are okay with eventual consistency. So that goes back to that concept that as long as a write is, okay, I should, so they have this, there is this concept of, quorums. So let's say if you have a 100 node cluster, and if you are having, I'm just picking random numbers, and if you are maintaining, let's say, writes on or replica on, let's say, 5 nodes, right? Now what you want to do is you want to make sure that you write to, when you submit a write, you write to at least 3 nodes in your replica. And when you read something, when you want to read data, either you can get stale data, or what if I tell you that when you submit a read query, you also want to get a response from at least 3 nodes in your application, right? So 3 for write, 3 for read. So what does that kind of tell you? If you have 5 node replication cluster, and I'm saying that you are always going to write to 3 nodes, and when you're reading, you are going to wait for data from at least 3 nodes.
So this tells that like at least those 3 nodes agreed on the data, and that should be the right data.
Can you elaborate on that?
Like for example, 3 nodes is the the kind of majority. It's like elections, right? It's the half of the population plus 1. Right. So like this can be, let's say, we cannot have a draw here. Like the other 2, no matter what they say, the first 3 guys, you always win. So yeah, they should be the right, let's say, they should have the right, let's say, data.
Right. So it can be basically not just the first 3. If I have like a replication cluster of 5, I'm saying like any 3 who responds to me, I'm going to pick the latest value from them. So I think you're kind of hitting this right point that I want to highlight there. So if you have 3 writes and 3 reads, that means at least one node is overlapping.
Yeah.
Right. That means that even if when I'm writing, I wrote to 3 nodes, and when I'm reading, no matter which 3 nodes I read from, right, I'm always going to get one copy, which is the latest version.
Yeah.
Makes sense.
Shouldn't we get the same value? Because if we read from 3, all the 3 nodes should give back the same value, right?
Yeah, let's say if you have A to E, right? And if you wrote to A, B, C, right? Yeah. And then you read from C, D, E.
Yeah.
Right. And let's say the replication hasn't, like the nodes haven't synchronized completely.
Yeah.
B and E won't have the latest copy.
Yeah.
But C will have.
Yeah. So in that case, would we check the timestamp of the latest one, or how does it work?
Yeah, we can check. I mean, timestamp can be one way, but the idea was that how do we ensure that at least we hit one node which has the latest copy? But to your question about how do we resolve this, that can be, possibly timestamp can be one way.
Yeah. So I mean, my question is like, why do we want at least one node to be overlapping between reads and writes in this case? Then is it for resolving only, right?
Sorry.
So in this case, like where we do like replication, like the read replication is 3 and the write replication is 3 replication factor. So at least one node would overlap for reads and writes.
Right.
The reason why we want to have at least one overlap is because they would get resolved eventually using timestamp or anything like that. That's the reason, right? Okay, makes sense. Thanks.
Yeah, I mean, you would always get at least one latest, right? Yeah.
I mean, you won't get any stale data then, right? It's a way to guarantee that.
Yeah, but I think I want to correct, just be clear here. So we did talk about eventual consistency, right? So given that you're not trying to make your whole replication cluster in sync at the same time when it was written, right? Let's say data was written, not all copies can be, needs to be synchronized before client gets a response back. But I was getting more onto the idea of sloppy quorums. I'm jumping a little ahead. I'm going to come back here. It's just like how I'm thinking around these concepts. So yeah, let me just bring this up. Yeah, so what the idea is that we want to maintain highly available writes. So let's say you have this 5-node cluster and replication cluster. You have more nodes in your cluster, right? Let's say 10 nodes, and you have replicated your data on 5 nodes. Now, let's say for some reason, and you are saying your policy is that I want to hear back a response from at least 3 nodes, for example, right? Before I confirm the write. Now, let's say if 3 nodes in your replication cluster are down, right? So you have a 5-node replication cluster and 3 are down. So you only have 2 available to write, but your policy requires 1 more. Now, since you don't want to decline the write, right? You never want to reject a write. So what they do is they adopt this idea of sloppy quorum, which means that, all right, I have 1 less node before I can tell the client that it's successful, write is successful. So rather than rejecting, I'm going to pull one healthy node from outside my replication cluster, right? So out of 10 nodes, 5 are replication cluster. So I'm going to pick a healthy node, let's say node 6 from my cluster, and I'm going to write to it so that I have the consensus, like 3 nodes I have written. And then I give confirmation to the client that, okay, data is written. And now when, let's say, that failed node, one of the failed nodes from your replication cluster comes back, this 6th node will actually, basically this 6th node will store some hints, some additional metadata within it, which tells it that, okay, this is just a temporary data that I'm holding. When, another node contacts me, I need to hand this over. So this is not like my data, I need to hand this over. And this is where the idea of hinted handoff comes in, right? So Dynamo basically is using this idea to make sure that it can survive temporary failures of nodes and not having to reject the writes from the client.
So what happens if you are not, let's say, able to pull a node out of the replication cluster? Reject the write? I mean, what do you do?
So say it again. Let's. What do you mean?
Yeah. So in your example, right? Let's say you lost one node, and then you just said, okay, now I'm gonna put one node that is not part of the replication cluster, but that, let's say, for a short amount of time, you'll be receiving the data.
Yeah.
Now that's fine, but let's say that like I don't have any other node outside of my replication cluster. I mean, I'm not able to pull any other cluster. What I do?
Right. So you are saying that how are you going to support writes if you?
Yes, exactly. Because you mentioned it like you don't fail the write because you are able to pull another node, right? So now the situation is you are not able to pull another node. I mean, what do you do?
Correct. That's a great question. So my understanding is, first of all, when you're defining your replication clusters, right, you tend to, so I think what the scenario you're pointing to is, consider the case when you're, let's say, the nodes outside your replication clusters are down or something, right? For what reason? I think that will come back to maybe this idea of handling permanent failures. I mean, first of all, in general, the way we would define our replication cluster is possibly like a small size compared to your whole cluster, right? If you have, let's say, 10 node cluster, you don't want to define your replication cluster to be possibly 8 nodes, right? Because that leaves the pool of, the cluster outside your replica to be very small to sustain this. But at the same time, I think if that happens, because it's not like it can't happen. So I think that's where possibly this idea of handling permanent failures might help. Because what this talks about is that, like you mentioned a scenario where you don't have a healthy node that you can pull, then how do you handle it? I'm thinking, is this something in general we would, like if you have 100 nodes, let's say, and you're maintaining replication of 3 or 5, the probability of like all the nodes, rest of the nodes to be down is like how, in general, how distributed systems handle it. I guess we try to reduce that probability, right, if all the nodes are down.
Yep.
But conceptually talking about the question you raised, right, I'm thinking around those lines. I mean, this thing is a little different, 4.7, but does anyone else have any other ideas on what might be going on in that situation?
Can you repeat the question?
Sorry.
Can you repeat the question? Like what exactly?
Yeah, I think the question was about that. We talked about this idea that if you don't have the like the quorum for write in your replication cluster, then sloppy quorum basically allows you to pull a healthy node from your, outside your replication cluster that you can use temporarily, right, for write, and then you give it back. But his question was, what if I don't have a node available that I can borrow? right? Then in that case, like, would the write be rejected? I mean, given this algorithm, or how does Dynamo handle that? Because it never wants to reject writes.
Maybe take a node from other region, something like that.
Yeah, I mean, that is what my thought would be. Like, we want to possibly maintain.
I mean, if you think that you always have some other node available somehow, then it's exactly it's the same thing that you were mentioning before, right? You just pull this guy,
Right.
but like assuming that you don't have, I mean, you don't have another resource. I mean, why do you do
Yeah,
this?
actually, you know what? Yeah, that would, we can think of this situation as, what if I set my quorum to be 1, right? As long as I write to one node, I'm good. And what if I don't have any node available, or a hypothetical scenario, right? And they do mention about it that to avoid that, they want to do this quorum thing. Yeah, so like it says, applications that need the highest level of availability can set their write to 1. And however, in practice, most Amazon, yeah. I mean, I think the way I read this is they are trying to handle that situation by saying that maintaining a certain replication factor, which would ensure that you don't run into that kind of situation.
Yeah, I think so. Yeah, I think so. Because
But I
otherwise,
think
yeah.
there will be a lot of replication in the clusters also, right? So there will be redundancies, cluster redundancies also, right? So maybe one or the other cluster will surely be handling that, right?
Yeah, like they make sure that they have at least one node available. Yeah, otherwise it will be, yeah.
So I have a question here. So when you say that it'll borrow a node, basically it's borrowing a node from another replica set, right? Because everything in that cluster is already occupied.
Yes, yes.
Okay, but what if that already has an operation going on it?
That is similar to what the other question was, right? For whatever reason, let's say you can't borrow the other,
Okay.
right?
Yeah.
Yeah. I mean, usually given your cluster and your configuration, you want to, have that, that this situation doesn't happen. You have something available. And also the other point is, like it says here, hinted handoff works best if this situation, node failures are transient, right? It just happens and comes back. So it's just one of the ways of it, but yeah.
So I was taking a look at on Stack Overflow. Someone has posted a same question. So what happens is the client would not get a success message once it writes to 2 nodes when the replication factor for write is 3. But then those 2 nodes will still have that data. And then whenever you try to read for this particular key, you wouldn't get and if let's assume that the read replication is also 3, in that case, the client would not be getting the latest one because it's being written to only 2 nodes, right? And what happened? And while this is happening, then Cassandra or Dynamo would perform some read repairs in the future where the latest return value to the 2 nodes would be removed, and because it's not honoring the quorum.
Makes sense.
So in that case, then it's like Dynamo is actually rejecting the write.
Yeah, that is what my question was. Like, Dynamo's main premise is that they don't want to reject write.
Yeah, it's highly available for writes, right? Yeah.
Yeah.
I mean, you would get, it's highly available, but it's not consistent. You would get a value for that particular key, but it might not be the latest one. That's the whole point of the eventual consistency.
This makes sense, yeah.
But what you said, like, effectively, you are missing a write.
Yeah.
Right? Yeah. Okay.
Yeah. Based on the concept, yes, you would be missing a write. But going back to Amazon's promise, like Dynamo's promise about never missing a write, either that can be a one-off situation where they do that, like, looking at the 99.9 percentile.
Yeah, exactly. Yeah, I think like I think the word shouldn't be like say never. I mean, it's like ever in the 99.999. You still have a chance.
Right.
The book Designing Data Intensive Application he mentions that we need a minimum number of available nodes
Yep.
to
Right.
support our rights. So we can't afford to lose all the nodes or go below that minimum.
Exactly. So that's the idea of quorum, right? You don't
Yeah.
want to confirm right unless it's written to W number of nodes. And similarly reads. Yeah, that's the idea of quorums.
Yeah, and the system should return an error if the quorum cannot be met in the case of a write.
Yeah.
I don't think it's always, I don't think any database would guarantee 100% rights, right? Especially in the distributed world.
Yeah, that's why like 99.9.
0.9, yeah.
Right. Yeah. So, okay. So great discussion. Thanks everyone for participating. So now I think we are kind of hitting on time, but this is very interesting. I found of how they are talking about. Maybe I can quickly talk about it and then handle this. But the point is that we talked about this sloppy quorum and hinted handoff, but this is more of a strategy to deal with the node that went down and then it comes back, and so it's like temporary failures. But when you are talking about permanent failures, right, and you want to handle this replica synchronization, at that time their protocol is different, and it's they use this idea of Merkle trees. And the high level idea is that you have two nodes, right, with a certain set of data. Now you want to compare, right, what is it that one node is missing versus other. And you want to make sure that you don't have to scan all the data that's present on those two nodes, right? So there is this idea of Merkle trees, which actually helps you catch where did the two nodes diverged in a cost effective manner. Rather than scanning all the data, you just scan a subset of data. And the way that happens is each node maintains a separate tree. And what this tree does is that all the leaf nodes of the tree are actually the hashes of the keys that can be present in that node. So we talked about this partitioning idea, right? Each node is responsible for a set of keys. So this tree on that node will maintain the leaf nodes, will be the hash values of the keys. And then the parent of those leaf nodes will be the hashes of its children, and so on. So that's how the tree is built. Now, when two nodes are talking to each other, what they'll do is they'll compare their root value. Now, if the root value matches, then you're sure that rest of the tree is the same because it's based on the hashes of its children. But if there is a mismatch in the root value, then you take it like, step by step. You then move to this one of its children and compare that. So that way, the idea is that if you want to actually detect where did my two replicas, diverged. So this is the data structure that they use to detect those inconsistencies. So this, I mean, I read it for the first time, but I thought it was a pretty interesting idea.
Yeah, really interesting. And one question, is this like a kind of binary tree, or I mean, what is this actual tree? I mean,
yeah, like the fan out thing, right? That they haven't mentioned. I probably would have to read more about it. At least here, they don't mention the fan out, like if it's a binary or an n array tree. Yeah, something to check.
Okay. Yeah, that's really cool.
Yeah. So, okay, so I think that was one idea. And the other thing very quickly is also when you talk about these data structures like trees and, data stores or databases, one of the big things is you want to minimize the amount of data that you read from your disk. So this kind of data structure also helps there, right? You're not reading the whole tree, just the branches you need. Yeah, so that was that. I didn't have time to talk about this replication, which was talking about these vector clocks, but maybe we can take that, a separate discussion on the, chat group. And but does this, like, some of the concepts at least made sense?
Yeah.
Yeah, very much. Actually, it relates to what we were reading in the book club, right?
Yeah, that is one of the things that was the goal of reading these papers, that how do you map those concepts to something in the real world production systems.
Yeah,
Um,
absolutely.
Yeah, this is really good. Thank you. Thank you very much for sharing.
Yeah, absolutely.
Sure, thanks
Thank
for
you.
coming up. And one thing, I don't know